It's my Zoom. All the consent rules in my Zoom.
Yeah, let me open the document.
Hold on, let me turn on my fan. It's really warm today.
Okay. Okay, so I have 4 FRQs. And yeah, like I said, we don't have to do all of it, but it's just, I just got the material together. Okay.
Can you zoom in so I can see? Yeah.
It's a little bit blurry, so I don't know.
It's fine. I think we can understand it for the most part. Can you start off? Because I really, I think I'll need some sort of momentum to get me going. Yeah.
So basically, there's 100 grams of water, and then there's also 10 grams of LiCl, right? So add both of those together since it's a combined solution. So 110 grams to start out. Like the formula is Q equals MC delta T, right?
Yeah.
So that's mass times specific heat times change in temperature. So mass is 110 here. And then change in temperature is also easy to find, 35.6 minus 15, which is just 20.6. So, and then the specific heat, I guess the one that they gave us is 4.18. So we would just go with that one. So we do 100.
The magnitude of heat absorbed. Yeah, that's Q. Got it.
So 110 times 4.18 times 20.6, and that's 9,471, 472 approximately. Yeah. And that's in joules, right? So
yeah, 9,472 joules.
Yeah, and then so I guess we would put it in scientific notation, so 9.47 times 10 to the third. And then, okay, the next part, determine the value of delta H for LiCl. Let me look at the formula again. I forgot.
From the way I got through these problems was by looking at the unit. So the unit is kilojoules per mole of reaction, right? Yeah. So we have, what we have here is the magnitude of heat absorbed by the solution itself. So if you write out the reaction and then probably figure out what it is per mole of reaction, I think that'll give you the answer for enthalpy of solution.
Wait, also we didn't figure out if it was, oh, never mind, my bad. It's absorbed by the solution. It says it in the question. Okay. So yeah, so we have 9.4719 kilojoules, and then I guess we divide that by moles of LiCl. So let me see what that would be.
We need to make sure that it's a 1-to-1 ratio at which it reacts, though, right?
Yeah. Probably.
Because otherwise, if you have, say for example, you have 3 moles in the reaction, then you'd have to divide by 3 to get per mole of reaction. So
I think it's just 1
mole. Okay. So since I guess we have 10 grams of LiCl.
This is for like this specific, wait, what is it? This like delta H is for this amount of LiCl. Like it's already proportional.
I see. Okay, I understand. Got it.
So
okay, so there's no, you don't have to worry about the mole ratio.
No,
here, right?
you don't.
Got it.
Because if they gave you one and they said it was for like 1 mole, then you have to look at it and make sure.
Got it.
This is for this specific thing.
So what's the molar mass of LiCl?
Apparently it's 42.394. So let's divide.
Just do so just divide our answer before in kilojoules over that number you just said, right?
Yes. So let's see what that gives us. Wait, no, we have to divide 10. We have 10 grams of LiCl.
Mm-hmm.
So we have to divide.
Sorry. Yeah.
We have to find the moles. So
Okay.
10 over, it was 42.39, let's see.
Grams per mole, right? So
Yeah.
Okay.
So
I have an answer.
I got 0.2359 moles, and then so since you have kilojoules and moles, and the answer is supposed to be in kilojoules per mole, you divide. So you divide 9.4719 over 0.2359. You get about 40.2.
Yeah, that's what I got as well. 40.2 kilojoules per mole reaction. I put the whole thing. So do you generally? I mean, I'm just curious. Do you like do all the intermediate steps and then finally do the calculation, or because what I do is I just
put do the entire
yeah, I do it all.
But I just like for the sake of explaining, I just
did
separately.
Okay.
Okay, so the next one. Oh yeah, also please ignore the notes. I got this from a different website. It's fine. So we have this.
Okay, so please remind me because so a reaction can be driven by enthalpy, entropy, or both. I vaguely remember what that means. So so enthalpy means if it's exothermic, that's energetically favorable, right?
Yes.
Okay.
And
if it's endothermic, that's means that that's not what's driving the reaction. Entropy means if you have more disorder on the right side of the equation, then that's what's driving it, right?
Yeah.
Okay.
And then also what's important to remember is delta G equals, where's the formula? I just saw it. Delta H minus T delta S.
Okay, that's right. So that's
so delta G is Gibbs free energy. Delta H is enthalpy, and then minus T temperature times delta S entropy. So what we have here, I don't even know if we have to use that formula for this, but that's just important to know.
And then so negative delta G means release of free energy, right?
Yeah.
Okay.
It's spontaneous.
Yes, for spontaneous, yeah.
Okay, so it says the flask gets cooler, and as the note says, that should indicate that it's endothermic because the reaction is absorbing heat from the surroundings, which in this case is the flask. So that should be plus delta H, like it says. So what drives the chemical? Oh, did they already do it? Yeah, I guess they did. They circled it for us.
Okay. Yeah, it would have to be entropy because it's not entropy. So we have to justify it based on the standard Gibbs field. So I forgot this as well. Can you remind me what it means to have standard Gibbs free energy versus just Gibbs free energy?
What do you mean by standard? I don't think we.
The little circle on the top indicates that it's standard Gibbs free energy. I think that means it's per mole or something. I can't remember. Let me search it up real quick.
I think it's just saying it can't be. So what's driving this reaction can't be the enthalpy because it's endothermic, which means it's like that's not spontaneous, like on its own. So what's driving this reaction has to be the entropy, meaning because it's endothermic, it just can't be that's making it spontaneous. So that's why it's entropy only.
Yes, Gibbs free energy. All this stuff is just it's molar entropy and molar heat. It's just like we did in the last problem where it's like per mole of reaction. Standardized just means it's per mole. But I think for this, would you have to actually calculate? I think you would probably want to show that equation that's delta H, right, minus T delta S.
Yeah, I would do that.
Okay, and so then you would explain that the S term would dominate, I guess, because it's negative, and then the H term would be positive.
Yeah.
Okay.
If the H term is positive, then delta S has to be a big positive number to make up for that, to make delta G negative. because if it's negative, then it's favorable and it's spontaneous.
Got it.
So that should be like basically your explanation.
Now, also this temperature here, is that change in temperature? Is that, what is that? Is that final temperature? I can't remember.
I'm not sure actually. We haven't really used the formula. It's just
Okay.
like
Sure.
I'm not sure. That's actually a good question. I don't know.
Okay.
I'm
gonna clear my,
okay. So we have this one. So we need to change the temperature from 298 to 933. So that should be 635 Kelvin. And yeah, let me look at this for a second.
I'll just write it on the top. Anything you're citing out, like just mathematics.
Yeah.
Oh, they did that here.
Yeah. So we're doing 1 mole, and we have 24. Like the molar heat capacity is it's molar, so it's fine that we're using 1 mole. We don't have to convert it to grams or anything. So 1 mole times 24 for the specific heat capacity, and then times 635, which was our delta T. So
because the moles and moles would cancel with that, so that you'd be left with 24 joules per Kelvin, and you'd multiply that with the 635 here to get rid of it. So this is your Q equals MCAT, right?
Yeah.
Okay.
But it's also, they gave us the heat of fusion, so I'm guessing you have to multiply that by your moles as well.
The heat of fusion is the heat. I think we're dealing with the heat capacity, right? Because we're trying to.
I think you need both.
You need both? Okay.
Yeah.
So we're starting with solid aluminum and we're melting it, right?
The heat of fusion is specifically what's required to melt it, but then the change in temperature is for. The change in temperature is a separate thing from the fusion one. So you need both. Okay. So we have the 1 mole times 24 times 635, and then you have to add that to 1 mole times, well, it says 10.7 kilojoules. Let's just convert that to joules.
Sure.
So 10,700. So you just add those together. So 10,700 plus what we got in the one before, which is 15,240. Did you get that too?
24 times 635 plus 10,700. I got 25,940.
Yeah, I meant before I added them together.
Oh, like, okay. Got it.
So 25,940 joules.
About 25.6 kilojoules.
No, 0.9.
Oh, sorry. I don't know what I was thinking. 25.9 kilojoules. Okay.
Yeah.
Can you explain why why we're doing that with the heat of fusion?
I think it's just because the change in temperature is separate from like the energy it takes to actually separate the molecules when it's melting.
Okay. The heat of fusion. Oh, I see what you're saying. Because you have to like
first you
get
change
across.
The temperature.
Got it.
First you change the temperature, and then there's a period when it's like the molecules are actually separating.
Yeah, you have that graph that looks like, I can't remember. It looks like that. And
it looks like that, yeah.
I understand what you're saying.
The part where it's flat is the fusion part. And so
you actually have to cross that to actually melt it. So if you don't do that, then you're just kind of at that tipping point where nothing happens.
Yeah, exactly. So you need both. Okay, so then the equation for the process, I'm going to read in my head.
I'm going to write down the answer we had in the last one just so we can compare it to this one.
I'm not sure how to start with this one, actually. Let me think.
Okay, I think can you unclick the picture in the bottom so I can see what it says?
Unclick, oh, my bad.
Yeah.
Okay,
okay.
I'm sorry. I don't know what's happening.
It's okay. Okay, so we're trying to extract aluminum from Al2O3 over here. And the standard enthalpy of this reaction is 1675 kilojoules per mole of reaction, right?
Mm-hmm.
So per mole of reaction, we get this much. Now, this is going to give you 2 moles of aluminum, right?
Yeah.
So to get 1 mole of aluminum, I think you would divide by 2, right?
Yeah.
Divide this by 2. So then
okay.
Get delta H for 1 mole of aluminum, you would do 1675 divided by 2.
Yeah.
And that is how much? About 8 something. I might be doing something wrong because this would be 837.5.
Yeah. Yeah, that makes sense.
Joules, but that's like
kilojoules.
Oh, kilojoules. Oh, okay, never mind. That does make sense. So how come this is way more than that one?
I just don't understand the question. What does it mean by like recycling?
Oh, what we did in the last one was recycling existing AL.
What does that mean? I don't know.
We're taking impure aluminum and we're recycling it by purifying it. Well, so it's basically, this is a very common question type. They ask you to compare this process using this other chemical reaction versus just taking impure aluminum and then melting it to purify and then evaporating out the impurities. That's recycling versus this using this chemical reaction.
Oh, okay. So then, yeah, so it takes much less to recycle than the 20. We had 26.
But this seems very fishy because why does it take so much more to? I
don't know.
Should I search this question up online and see if we can find a solution?
Yeah, sure.
Okay. Scrap metal by melting the metal to evaporate impurities. Calculate the amount of heat needed to purify 100 mole. Okay, that should be enough to switch it up. Oh, it's on Chegg, and I'm not going to get a subscription.
Let me look
here,
it up.
at least I can, yeah. Let's search that up. Oh, this is from 2015 AP Chemistry, I think.
Okay. Yes. We're right. Actually, it's 26 kilojoules and 837.5. So.
Oh, perfect.
It's just like significantly less, I guess.
Sure. Yeah. It's just that's what it happens to be, I guess. So I think really, even if you kind of don't know the exact formulas, and I think if you just look at the units, you can probably just kind of weasel your way through it. I think. Yeah. Especially with thermodynamics.
Yeah, I think that's a good strategy, honestly. Just like look at the units.
Sometimes obviously you do have coefficients, and you have to be careful about that. But if you're like, I'm just saying, like if it's like a last resort, if you don't know exactly.
Yeah. And also pay attention to like kilojoules versus like joules because that's very important. You're gonna get a much different answer if you don't do that. Okay. So.
Okay. Separate experiments with measures.
Okay.
The first one is propylene, right? C2H3Cl. Or is that vinyl chloride? That looks like vinyl chloride.
I think it's vinyl chloride.
Oh yeah. Okay.
Yeah. Okay. So
propene is which much? It's propene is C3H6 because it's meth, eth, pro, bute. So pro would be C3. Yeah.
Wait, how do you do that?
Oh, that's so so those are you have so when you have hydrocarbons, they follow a naming convention. We don't usually learn OChem, so I just know a little bit. So you have the suffix is either ane, ene, or eine. Ane is single bonds between the carbons and the hydrogens. Ene is double bonds, and then eine, like YNE, that's triple bonds. And then the prefixes are meth for one, so it's methane is C1H4. We just say CH4. Methane, then propane, then no, sorry, methane, ethane, propane, butane, pentane, hexane, and so on and so forth. Then the next few ones are predictable. It's the meth, prop, bute that always.
Yeah. Okay. So, using the table, determine whether the combustion. Okay. Okay, so
okay, I think we should probably start with the equation because that's probably the easiest, right? To figure out for 1 mole of vinyl chloride, you would just divide this by 2, right?
Well, I think it's asking for 2 moles anyway, so why not just like go?
Oh, it's asking for 2 moles?
Yeah.
Oh, okay, never mind. So then you don't have to do anything to that. Enthalpies of formation below. Determine whether the combustion of 2 moles of propene releases more, less, or the same.
Based on the, like, you know what I mean? Let me see if it works if I do that. So 37 times 2. And then.
So this is 1 mole. So 2 moles would be 2 times that, which is what?
It's 74.
74 kilojoules, right?
Yeah.
Oh, there's that law, right? I can't remember. What's that law where you add up? Do you remember what law I'm talking about, Neha? And you multiply the coefficients and somehow you have to add them up. I can't remember exactly.
Don't you just like it's in the table, it gives you the enthalpy of formation for 1 mole. So don't you just multiply by the coefficients?
Yeah, exactly. You would multiply by the coefficients. Yep. And then you just add them all together. So this is times 5.
But I tried that with the first equation and it doesn't quite match what they gave us.
That's the thing. I think that's what it's saying is this what is the combustion releasing more? Is this releasing more energy? And you have to compare. It's probably not going to be the same. It wants you to compare this with the data in the table. So what do you get when you multiply out the coefficients? So like if you do 5 times
I tried it like everything from the first equation is in the table. So I did that quickly and it's not quite the same. Is that supposed to happen?
It's not going to be the same is what I'm saying. Like they want you to compare the two. Like
I thought they were asking us to compare the 2 equations.
Oh, I didn't even see this. Okay. Combustion of 2 moles of propene. Oh, I'm completely sorry. Okay, I'm misunderstanding this. So we need to see whether the combustion of propene, 2 moles of propene here releases more, less, or the same as 2 moles of this releases. Okay, so 2 moles of vinyl chloride releases this much.
Yeah.
So we need to figure out how much 2 moles of the combustion of 2 moles of this releases. So C3H6.
I'm not sure why it didn't work.
Well, it's not. Once again, it's not going to be the same if you work it out with this. So this should be.
Why isn't it the same?
For if you calculate the one for propene.
No, I mean for, like I did the thing for the
for the upper reaction.
I got 2,170 instead of 2,300.
I don't think. Yeah, you're not going to get an exact answer. It's. I think they're putting these numbers here to throw you off, like with the C2H3CO.
Oh, okay.
They want you to use this data up here, and then they use the data only for propene, the reaction.
Okay, so we have positive, so 21 times 2, so positive 42, and then we have 6 times negative 394, so that's negative 2,364. And then we have 6 times H2O, so 6 times negative 242, which is 1452. Negative 1452. So
Yeah.
just add those together. I got 3,774. So it should
negative, right? Negative
yeah,
3,000.
Negative, yeah.
Negative 3,374.
774.
3,374.
No, 774.
Wait. So, oh, sorry. I see what I did. Negative 3,774.
Yeah.
Okay. So that's for the entire.
So it releases more energy then, right?
That's delta H. So this, yeah. Another thing to be careful of is usually in these questions, they ask for the magnitude of the heat release. They're not asking for, some people get confused because they'll say this one releases more energy because technically the number is greater. Do you understand what I mean? Because they're negative numbers, technically this answer is greater, but the magnitude of the heat is, just be sure to look at the magnitude of enthalpy and not the actual value of the numbers themselves. That's a common mistake on the AP exam from like previous years.
This is really weird. I was looking at, I just like checked the answer with like a key, and like they got the same as us. It releases more energy, but they somehow got negative 3,858. But they did the same exact. They did the same exact like formula. I mean,
maybe it was just a calculation error, or maybe it was either us or them. Someone did a calculator. Yeah, but the methodology of what we said was right, I believe.
I checked it again, and I did the exact same formula. I don't know why it's different. Okay.
But everything we've done so far, these are pretty common FRQ style questions. Like these, I remember even last year's AP exam, they did like they had an enthalpy question. It was exactly like this.
Was it like this like recycling thing?
Yeah, I think it was the recycling thing, and also remember it was like last year they made it extra long, so they had like up to like part J, K, L. Yeah, it was
really?
crazy.
That sucks.
Yeah, it was.
Wait,
so they combined this with entropy, enthalpy, and also bond energy, and it was a lot. It was
bond energy. Yeah. I think we're doing that next, actually, like tomorrow. Okay. Wait, can you explain the recycling thing again? I just didn't quite get it. The
second thing, like
what is recycling it again? Like just purifying it?
Yeah, you don't need to understand what that is. It's just asking you what this question is saying is which is requiring less energy. Is it the first method, first process in part A that's requiring less energy, or is it the second process that requires less energy?
Okay.
Yeah, recycling just means taking existing aluminum that's impure and then, recycling it to create purified aluminum.
Yeah. Okay. So now on to multiple choice. Bond enthalpies. We're learning this tomorrow, so I don't know.
Let's use. Actually, you could probably do this with some just brute logic. I think here.
Okay. I just know one of them is a triple bond, so that's all I know.
Oh, okay. Well, I wasn't thinking in terms of that actually. I was thinking in terms of electronegativity.
Oh, really? Okay.
The reason why is because if it's more electronegative, it probably holds more bond energy, bond enthalpy, or whatever.
Bond, yeah, okay. I think it also has to do with the like the triple bond thing. I think it has to do with that too. Because when we look at like there's this graph, it's like bond potential.
Oh, yeah, I know exactly. Yeah, they refer to that graph, and I remember I couldn't solve that problem. So it looks like this, right? It looks like a dip, and then
yeah. So I guess from electronegativity, it would be A. Does this change when you look at triple bond?
I thought it would be C. Because if it's more electronegative, it's more attractive, right?
Yeah, my bad.
So I would.
My bad, yeah, C.
Okay, I would choose C. Do you have an answer key for this?
Yeah, I do. Let me check. Okay, they said A. I don't know why. It should. I was thinking C too. Like I just mixed up the like greater than and less than thing.
Yeah.
It should be C, right? Because wait, which one? Hold on. Let me look up F2, the bonds. Oh yeah, so F2 is a single bond, and then O2 is a double bond, and N2 is a triple bond. So I guess that's why.
So it just has to do with the number of bonds.
Mm-hmm. Yes, N2 is a triple bond, so that is why. You have to look at that when you're considering this.
So because so N2 has a triple bond. And just for extra, just to clarify something, more bonds means shorter bond length, right?
Yeah.
Okay.
Okay. I don't know what this means. I don't know what that means.
Yeah, I don't know what D. Oh, delta. I think that's trying to say delta because they couldn't type out delta.
Oh,
delta,
okay.
yeah. Change in standard free energy.
So decomposition is breaking bonds. So breaking bonds requires energy. So probably not spontaneous. I don't really know. That's endothermic. But
yeah, I have no idea.
okay. But then also, if you separate them, it's more disorder. I don't know.
That's true. Yeah, I think that's something you kind of have to. That's one of those like you kind of just have to know. What is the decomposition of H2O2?
I don't know.
Okay, let me search it up. H2O2. The decomposition is exothermic.
Why? Isn't it breaking?
Well, this chemicals.co.uk. We all know that the British are right about everything, so we're gonna follow this website over here.
Okay.
So when it comes to determining why hydrogen peroxide decomposes so easily, we have to look at the chemical structure. It has a single oxygen-oxygen bond. The peroxide bond is incredibly weak and unstable, so it decomposes into water and oxygen, right? So this decomposes into H2O plus O2. I'm not going to balance it right now.
Okay,
Either way, yes, it'll be more disorder and it's exothermic. So the Gibbs free energy then would have to be less than 0.
Yeah, but what's KEQ?
That's your equilibrium constant, right?
I forgot what that is. I don't know.
There's an equation on your formula chart that relates, I think, the two.
Oh, okay.
Is there?
I don't know if we learned this yet.
AP chemistry formula chart. Because yeah, I need to look at that again. But as far as I can remember, if your equilibrium constant is greater than 1, then that's suggesting that the forward reaction will proceed. And if it's less than 1, that suggests that the reverse reaction will proceed.
Oh, right. Okay, now I remember. Yes. Okay.
All this stuff I'm saying is from vague memory. So
no, yeah, you're right. No, we did learn this. It just like looks weird when they wrote it like this. Like I don't know. Yeah. So I know what it is. Yeah. So since I guess the forward reaction will run, so it should be C then.
Yeah, I think it would be C.
Since it's so, but like I don't know how I would have known that. Like I didn't know it was so spontaneous.
That's one of those things you know from just kind of like if you're in a lab and you're doing like experiments, H2O2 is such a common chemical you work with that you would know. Now, obviously, I know you're taking a class and you're not like.
Yeah. Okay.
Yeah. So I don't know how exactly you would know that, but.
I guess if you look at that it separates it. Okay, I can't talk. If you see that it separates into H2O and O2, that should indicate that. And also, like, is H2O2 a strong base or acid?
Oh, wait, I didn't even think to associate bases and acids with hydrogen peroxide.
It should be a base, right? I don't know. I have no idea.
Hydrogen peroxide is. Let's see. Okay, so like the first thing, if you search up the Wikipedia page, it says the first thing is that it's a very unstable. It's slowly composed in the presence of light. Like the whole, yeah, it's known for being unstable.
Okay, so then that would push the reaction away from.
Yeah.
Okay, yeah. So it would. Okay, yeah. I'm not gonna try to explain.
It's one of those things you just have to know from experience.
Yeah,
You know?
yeah. Okay, so yes. There's no table above, so I don't really know.
Oh.
Wait, is there a table in the place I got it? There's no table, so. Oh, wait. This was in our homework, and yeah, so I don't think I have to explain it. It was in our homework from before. Okay. What is D? Delta. I keep forgetting. Okay.
Yeah.
Delta H.
Yeah, you're gonna see an actual delta on the exam. You'd never. I think this person was just trying to type it out. So.
Yeah. I think these are AP classroom problems, and I guess they had to type it out on Quizlet, which is where I got it.
Oh, the some of them are titled so funny. They're like called "You'll Remember."
Really? No, mine was very normal. Mine was just AP Chem, kinetics and thermodynamics. So yeah, I guess you just do 26 minus 26, and then times specific heat, right?
So you're just doing Q equals MCAT here?
I think so. And the specific heat isn't joules per grams, that. So, and it gave us the density here, and we have milliliters, so I'm guessing we have to convert it into grams.
Yeah.
So it should be like 10.
10 milliliters. Yeah, 10 milliliters times 1.
10 plus 10.
Gram per, yeah. So the mass is just 10 grams in that case.
Isn't it 20 if you add them together?
Oh, sorry.
I mean, I'm asking. I don't know.
Yeah. I think, yeah. This is grams per milliliter of NaOH. Okay. Well, yeah, it is 20. I'm not gonna do the math rigorous. I can't like write it out because it would take too long. But reason being this, it's 1 mole per liter of NaOH. Wait.
This is just.
I don't think we use the density.
But don't we need to convert it into grams to use this one?
Yeah, but the way we would get that is from the molar mass, I think.
I think if you didn't, well, okay.
Well, if they give you 1 molar NaOH, you know that's 1 mole per liter.
But why would they just give us density though? If maybe it's to, I don't know.
Maybe it's to throw you off. Maybe you have to use it. I don't know. My initial reaction would be to do this and say that that's 1,000 milliliters on the bottom, multiply that by the 10-liter sample.
Also, these are all negative. Doesn't that indicate that it's exothermic?
Yeah.
But the temperature increases.
Yeah, that is exothermic, right?
Why?
Because if the reaction is if when you measure it, it gets warmer, that indicates heat was released. And this is the crucial problem surrounding thermodynamics. Is it's hard for us to wrap our mind around this idea that if it gets warmer, that doesn't mean because heat was lost, that's why it got warmer. Rise in temperature indicates it's exothermic, not endothermic.
So if ice melts into water, is that exothermic or endothermic?
Ooh. Ice melts into water.
Yeah.
That I think is endothermic.
But if you measure the temperature, I guess if you measure the temperature of the surroundings, then the surroundings should have gotten colder.
Because that requires an input of energy, right? Getting from ice to water.
Yeah.
That requires you to put in energy, and therefore that's endothermic. but obviously the
The surroundings would lose heat.
final temperature is warmer.
The surroundings would lose heat. I think that's why, because.
Yeah.
Right?
Mm-hmm.
Okay.
So you're saying this is endothermic here?
No, I'm saying, I'm just,
Oh, you're trying to account for that. Okay, okay.
Yeah. So anyways, it's, if you use what they gave you, I got 504 joules. So.
Using this method here?
Mm-hmm.
So you would get what? 1 over 100, which is 0.01.
No, I mean using the density thing.
Oh, using the density thing?
Yeah.
So what's the importance of the fact that it's a 1 molar solution? Does that matter?
Oh, yeah, I don't know. I have no idea. We could try, wait, try your way. What were you gonna do?
Okay, so that would have, you have 10 milliliters for 1 mole of NaOH per 1,000 milliliters. So zeros cancel, milliliters cancel, you get 0.01 moles of NaOH. And then that reacts with that same idea, so that's 0.01 moles of HCl.
Mm-hmm.
Um,
Do you want me to look up the molar masses?
yeah.
Okay, so HCl's molar mass is 36.46. And then
36.46. It's grams per mole, but I'm not going to write that out.
And then sodium hydroxide is just 40.
40 here. Okay.
Mm-hmm.
So if that's, so this will become 0.3646, and this will become 0.40.
Yeah.
Grams of that, and then grams of that. But that's hydrochloric acid, right? We just want to look at hydrogen, right?
Why?
Isn't that asking, that's what the question is asking, experimental value of delta H. Oh, sorry. Not hydrogen, that's heat. I'm so sorry. Yeah.
It's just weird seeing it like this. I don't know why.
Seeing it like that.
Okay.
Okay. So now you add these two together, I think.
Yeah.
Because it's a 1-to-1.
Mm-hmm.
The mole ratio is 1-to-1 in the reaction, right? Because it's just NaCl, H2o is the product, I believe. Or
yeah.
I don't know. Either way, it's a 1-to-1. So then the total mass is 0.7646 grams. If you multiply that by 40, if you multiply that by 4.2 times, how much was the increase in temperature? Or 6, right?
Yeah.
So what is that? 0.7646.
I didn't get like a good answer. It doesn't match any of the.
Oh, it's 192. That's not 193. That's not a good answer at all. So you just have to use the density?
I think so.
Huh.
But the density doesn't match either. I don't really know what to do about that. I got so if you do 20, right? 20 times 4.2 times 6 is 504. If you convert that into kilojoules, that's 0.5, and that doesn't match any of them either.
Well, that's because we didn't convert to moles of reaction. We converted to moles of.
Oh.
We converted to the total joules. But we have what the answer here that I got is 192.7 joules, and that's the joules for the what? Joules for this.
It's 19.27.
Oh, I got 192. 0.7646 times 40. Oh, it's 4.2. Yeah. Okay. 19.27 joules.
Okay, and then so if you divide that by so you convert that into kilojoules then?
I guess 0.
And then divide that by the moles?
19. Did I do that right? No. 0.19, right? 0.01927 kilojoules. And it's how many? It's 0.01 moles
0.01.
I don't know what's going on, to be honest here.
I don't know what this is. Because the answer is A.
The answer is A. Okay.
I don't know why.
How would that work? So let's see. Okay, let's try this one more time just with a clean mind here. So okay, so we know that initially we have how much? 0.01 moles of NaOH, right? And we have 0.01 moles of HCl. We need to get one mole of reaction, right? So if that's the case, why don't we just multiply both of these by 100?
Why do we need 1 mole?
Well, your final answer is going to be.
Yeah.
That's not going to help, though, is it? I don't think that's going to help because you're going to need to multiply.
I guess it does help. It does help because we got when I did it with the density, I got 0.504. So if you multiply that by 100, it's 50. So.
Oh, okay. That makes sense. So you start with the density, and then you use the fact that then you use this molar mass to find how much the reaction itself has in terms of moles, and then you use the fact that you have to multiply by 100 to get to 1 mole of reaction. So that's why you use. Okay. So what you did was you said 10 milliliters. That's essentially 10 grams, right? Then 10 grams of this. So that's 20 grams. So 20 grams. So 20 times the specific heat capacity, which is 4.2 times 6 happens to be 504.
Yes.
And now when you do the divide by, because you would multiply by 100, yeah, to get to that.
504, and then in kilojoules it's 0.5.
You divide by the, got it. Okay.
Okay. So, this is redox. I don't really know.
Redox reaction occurs represented by the equation below. Okay, I'm sorry, but I'm going to need to rewrite this as delta H because otherwise, you know what this makes me think of? This makes me think of like a differential of hydrogen. I don't even know. That doesn't make it like that looks like calculus and it looks like DH to me.
It just reminds me of, I don't know. It doesn't remind me of anything.
It doesn't look. That would be delta H.
So what I don't understand is why does it say 2NaO here if it says Na2O2 here?
Na2O2? Na2O2. I think Na2O2.
Oh, it's the same thing. I mean, I don't know. Maybe
yeah, essentially it's the same thing. It's 2 moles of, numerically speaking, it's the same thing.
Yeah, okay.
I don't know if they're physically the same thing.
They wouldn't, but I don't know. I guess they're just hitting it like this. I don't know.
Okay. 2 trials are run using excess water. Okay, so water is our excess reactant.
Okay.
First trial, 7.8 grams of Na2O2 is mixed with 3.2 grams of S. Okay.
So if it says they both yield the same amount of SO2. So I think that means that Na2O2 is the limiting one, right?
Can you walk through the logic?
Oh yeah. So they increase the amount of S, but the amount yielded is still the same. So that means we already had enough of S. Increasing it didn't affect anything. We had to increase Na2O2. So that's what I'm thinking. So limiting reactant we know, we think is Na2O2, and then Finding heat released for 2 trials. Okay. I don't know.
So we have to use Na2O2 because it's the limiting reactant. So since we have 7.8 grams, right? Convert
so
that into
0.1. We have 0.1 moles. It gave us a molar mass.
Where is it?
It's in the problem.
Oh, 78 grams per
yeah,
mole,
so we
right?
have 0.1 moles.
Of Na2O2. So this is like you said, 0.1 moles of Na2O2, which is the same thing as saying 0.1 moles of 2NaO, if that makes sense. Because we need to put it in terms of the reaction above, otherwise we can't. Right? So now what? Now we use this reaction up here.
Yeah, so what do we do with the delta S? I'm not sure what to do with that part.
I don't think we use that. I don't think we would need to use that.
Okay.
I think we simply use the
do you
delta.
just multiply 0.1 times delta H?
I think so, because that would get you about 30 kilojoules. Because 0.1 times 298 is about 29.
Okay, so 29. Let's see if it's C. Let me check. Yes, it is C.
It is C? Okay. So
Good
what we
job,
did.
team. Okay. The same one. I mean, the same formula. So which is reduced? I don't remember. I didn't study this part.
Okay. Reduced.
Oh, wait. Reduced is gaining of electrons.
Yes.
So which one gains electrons? Okay. So S is at 0 at first, and then when it's with O2, it becomes -4.
Well, the O2, it's the O here is -2, right?
But then O2, so -4.
So then S has to be 4
plus.
plus.
Yeah. Right? Yeah, I meant +4. Did I say negative?
Okay.
Okay. So it's not S then, and then and
S
it can't be. Oh, it couldn't even be that because it's gaining electrons. It could only be O.
I think it'll be O, which is because oxygen oxidizes, so it must be reduced. Usually speaking, not always. Well, to my knowledge.
Yes. So
here O is probably still 2-, so Na is probably 2+.
But isn't it in both? Like, how can you tell?
Well, here it would also be 2-, so H would have to be 1+. Okay. So in both of them, oxygen is 2-. So the net oxygen has a net of 4- here, and it becomes 2-, so that means it must have gained 1 electron each. Oh, but you're saying which element?
Wait, this formula doesn't even make sense. I don't understand it. There's 2 NaO on the left, and then there's 4 NaOH on the right.
Oh, it's not balanced? Maybe it's not balanced.
But why would they give us an... It's really,
that's
really weird. That's so weird. To give us like an unbalanced reaction with coefficients, that's super weird.
Well... Oh, okay. So
for it to make sense, it has to be 4 NaO.
Let's just make it 4 NaO for our sake. What about an NaOH? What are the numbers? O would be. Do we start with O or do we start with H when we're doing hydroxide?
Does it matter?
Oh, that's right. Okay. It doesn't matter because it's 1-, right? So that would be 2-, that would be 1+, and this would be
1+.
1+, yeah. So sodium actually seems to be. It's probably this one.
No, I mean, it can't be reduced. if it loses an
Oh,
electron.
because it's wait. It's gaining an electron.
But the explanation
Oh,
doesn't.
the answer choice says it's losing. What?
Yeah.
Oh, that's confusing. Oh my. Okay.
Wait, it's weird. Okay, wait. Actually, Na is +1, right?
Yeah.
That means that in NaO, oxygen has to be +1. I mean, -1.
No, but I'm saying I would start with oxygen when I'm doing oxidation numbers. In NaO.
Wait.
Here, let me see. Let's search that up. NaO what are they called? Oxidation numbers. I think, right? Yeah. Is NaO even a thing? It's I know NO not Now what is NaO? Sodium superoxide? Is that what that is? That might be a typo because I don't know what. Yeah, I can't find anything called NaO. That seems very weird because how do you have?
What is it supposed to be then? Na2O2?
Maybe, I don't know, or maybe it could be NaO2. I don't know. I've never seen what is NaO, because O has an oxidation number of -2 and Na has
+1. I don't really get this question, but it would be one of these because, well, it has to be one of these because that's reduction. And then I don't really know why there's a difference in like which one it's from, right? Because
maybe let's see. Okay. Maybe it's because the 2- here. This is I don't know. Can you check the answer choice?
Yeah, it was C. It's C.
C?
Yeah.
First of all, this isn't even, it's written as 2NaO2. This is why that's confusing. I think the reason being is this is 4, that would become,
writing something?
No, I'm writing it right now. So that would be, there's 4 O's. So I guess there's like a net of 8-.
Yeah.
8. Oh wait, if it's the way they wrote it, then it would be a net of 4-.
Okay.
And that becomes.
Oh, okay.
Minus.
I see.
But then couldn't you make the same argument
for
yeah.
H2o? It's really weird. I don't know.
It's weird. I don't know.
Okay, let's just move on. This question is strange. Let's just move on from these ones. I don't want to look at this formula anymore.
I think we might be able to do that one though. Let's just look at it real quick, and if it's weird, let's talk about it.
Oh, okay, maybe. So it would be, there's a positive delta H and a negative delta S, and so that would mean it has to be a positive delta G.
Yeah.
So it's thermodynamically unfavorable, right?
Yeah.
Let me check. They didn't even go. Oh, okay. It's C apparently.
Why?
But if it's a negative delta S, then doesn't that make it, because it's minus T delta S, so minus times minus.
Yeah, that's what I would have thought as well. So 298 minus 298 H minus T.
Is there a typo in this one too? I don't understand. This would only make sense if it was it was supposed to be negative 298.
Yeah, if that was a negative, that could make sense.
Oh, it tells us. I assumed that it's C because they put asterisks. So.
Yeah, that's what I was thinking as well. Okay, well, here's the thing. If it's written the way it is written, it's thermodynamically unfavorable. And if the correct answer choice is C, then that has to be it's a negative 298. Because if it's saying that it's driven by delta H only, that means delta H has to be negative.
Yeah.
Because negative delta S is bad.
We're just gonna ignore. There seems to be a lot of typos in this question, so we're just gonna move on. Okay, so let's see. There's no graph. I'm sorry, these questions are so weird. I think we can kind of guess, right? No, we can't. I don't know.
Well, if it's heated to liquid water and then to water vapor, here, look, so it's the main idea here is that it's going from ice to water to vapor, right?
Yeah, so
obviously,
so disorder is positive, and enthalpy, well,
okay, so let's go and eliminate A and C because we know entropy.
yeah. So enthalpy, it's endothermic. It's endothermic.
It's endothermic, right? I would think it's endothermic as well because you have to put in energy
to break bonds.
Yeah.
Okay. So that would be B, I think.
B then.
Pause. Okay, let me check. Yeah, B. Okay. Okay.
Do you remember Le Chatelier's principle?
No.
Oh my, that's very important. Like that shows up a lot. Like you want to definitely like that's something that's really helpful in the FRQs because you can justify why things happen the way they do using Le Chatelier. Stating that there are certain constraints. Le Chatelier's principle basically says if there's some sort of change, then the system will try to counteract that change.
Okay.
Or counteract the effect of that change. Yeah.
Mm-hmm.
So like if it's an equilibrium and I suddenly add more products, then it's gonna go in the reverse direction. So I go back to equilibrium.
Okay, yeah. I just guessed in my head. I thought it was C. It just seemed right, and it is C. So I was just looking, and delta H is positive.
Yeah.
And then since it's talking about like the vessel, it immediately made me think of like the surroundings. Mm-hmm. Right. So temperature must decrease.
Yeah, temperature has to decrease because it's endothermic.
Okay. Okay. So we have 1 mole thing goes.
I think you need a rice table for this.
What? Okay. I think it's.
Yeah, I think you need a rice table. I don't know how you would do this without a rice table.
What would. Okay. If they're returned to 600 Kelvin, what does that mean?
Well, if I had to take a wild guess, I would just choose C because initially there's P1 at 600, so I'm assuming at 600 you would also have P1.
I would choose D, but I'm not sure. Yeah.
Why would you choose?
Oh, it is D. I was just thinking because there's 1 mole here, and then there's 3 total here.
No, that makes sense. Oh, because it's going to completion? Oh, okay. Yeah, no, that makes perfect sense. Because you start with 1 mole, you go to completion, so now you're left with 3 moles for every 1 mole. And since the temperature we're keeping constant 600 to 600, that's not going to affect pressure. So that means it's 3 times P1. That makes sense. Okay.
Okay. We're going from 1 gas to 2 gases. I guess that's more disorder. Maybe.
Yeah. Excuse me. It's positive since what? Such weird.
Wait.
It does go to completion, so it can't be A.
Mm-hmm.
It must be positive since delta G. is negative.
Delta G should be negative, right?
Should be. Do we know that though?
No.
Okay, well, it can't be.
I'm thinking, yeah.
That doesn't make sense because how do you have more moles of products than reactants and then say it's negative?
Yeah, so I think C makes the most sense.
I think so too.
Let me check. Yeah, let's see. So basically, I just want to explain it. So because, well, I'm thinking since it's like 1 mole, it like breaks up, so it's more disorder. So I'm thinking it has to be positive delta S, so I would eliminate B and D. And then if it's positive, then, and this like explanation doesn't make sense because it goes to completion, so it can't be thermodynamically unfavorable. And so, yeah, I would say, and if that means it's spontaneous, so yeah, delta G should be negative too. Okay.
On the AP exam, when you're doing the FRQs, I wouldn't say spontaneous. I would say energetically favorable or energetically unfavorable.
Okay.
Yeah, when you're explaining.
Yeah,
it's a good, spontaneous is a nice way to think about it, but like technically, it's not that it's spontaneity. It's more about favorability. Okay.
Okay. We didn't learn bond enthalpies yet. That's the next thing.
Bond enthalpy is the energy required to form or break that bond.
Yeah. H2, that's just 1-to-1, right? Yeah, that's 1-to-1, like a single bond. That's what I meant. I don't know why I said 1-to-1. CO should be.
I see what answer choice D says.
Yeah, sorry.
All of the bonds in the reactant and products are polar. Okay, can we go back to the question? Or just that part. CH3OH is not all polar. That's you have a methyl group and then you have a hydroxyl group. CH, H, H. You have O. I'm not exactly sure what this would look like, but I think would that be a double bond?
There would definitely be some double bonding somewhere. There would it have to be a double bond from O to H as well? If
can't have a double bond from O to H, so would that
okay, right, my bad. Or you can do a lone pair on O.
Yeah, I think that would be a lone pair on O, right there.
Okay, so I think it'd be 2 lone pairs actually, since.
Oh yeah, you're right.
Okay, yeah.
That looks right.
So then there's only single bonds on here. So maybe I think the bond enthalpies of the bonds in the reactant is probably less, I would say, than the products.
I don't know. How would you know that? I don't know if you would know that. You could, maybe.
I guess I don't know.
Oh wait, maybe you have to use the fact that it's delta H is positive.
So that means it's endothermic. So
that means the products have more, are like kind of like a higher state, right?
Yeah.
Then the products have greater bond enthalpy sum.
Yeah. So it is.
It is B.
Yeah, I mean, let me check.
Yeah, using delta H, I think B.
Oh no, it says it's A. So.
It's A.
Yeah.
The sum of the enthalpies of the bonds in the reactant is greater than the sum of the bond enthalpies of the bonds in the products.
But that doesn't make sense to me. I don't know. If it's endothermic, then shouldn't it be?
It should increase, right? It's endothermic graphs are the ones that look like this, right? You start off like reactants here, go up, and then products here, right?
Yeah.
That's endothermic.
Mm-hmm.
So then the sum should be greater for the products then. Why is it saying that it's greater? Maybe bond enthalpy, hold on. Let me make sure what the definition. Bond enthalpy is what? It's the amount of energy required to cleave that bond, so break that bond. So it's saying that the reactants, you need more. Okay, I guess that makes more sense. Because if it's endothermic, that means you have to put energy into the system to break the bonds and this and then reform them into this. So you needed more energy.
Isn't that energy absorbed?
Huh?
Or is it, is that energy absorbed or is it used up?
Yeah, so you needed more energy to break that bond in CH3OH. And then form CO. Yeah, I think that's just a general rule is, and you can actually probably remember this rule is if you have an endothermic, that means that your bond enthalpy in your reactants is greater than that in your products. Because that logic should always.
Wait, what did you say?
I'm saying that this logic should always hold that if it's endothermic, then the sum of the bond enthalpies in the reactants should always be greater than the sum of the bond enthalpies of the products. Because the fact that it's endothermic means you're requiring more energy to cleave those bonds in the reactants and then reform them into the product.
That makes sense, I suppose.
Kind of. I'm just trying my best to find a reasoning why this would work.
Like, I guess if you think about the ice to water thing again, that's endothermic, and ice you can say has stronger bonds than water or water vapor. So you can think of it that way. Would that work?
I don't know.
Okay.
Maybe. No. I think I don't know if I would use bond enthalpy because bond enthalpy is like strictly like it. You know, CH has a specific bond enthalpy. CH has a specific bond enthalpy. It's like between two atoms. You know. Okay. Yeah.
Well. Yeah, but yeah, I guess you couldn't technically use that. Okay. Okay. So, 200 grams, and so I would do 8,400 over 200 over 4.2. 10. I got 10? Why did I get 10? Oh, the delta T is 10. So that means it's either 60 or 40. Let me think.
You said Q on MC was what once you do the math?
Huh?
Q on Q divided by MC is how much when you do the math?
Oh, 10.
Okay, so that means it's increasing by 10.
Yeah, so I would say it's 60. Let me check. It is 60. Okay.
Provided above. How nice.
Okay, well, moving on.
Based on the data, what data?
I'm so annoyed. Oh, is it just this data?
It is that data. Just that data in there.
Okay. Oh, we had this question for homework. We can talk about it. Huh?
I don't know. The problem sounds kind of sad. Just this one cashew's burned.
It's 1 gram. Well, okay. Actually, we can do this problem. It was in the homework. We can just go over it. So 1 gram was burned in a calorimeter containing 1,000 grams of water. So you do, I don't know, okay, I have a question. When do you know, like, when to add the grams of water plus, like, the other thing, like, in this case, the cashew? Like, would you do 1,001 or just 1,000? Maybe because this is the specific heat of water itself, you only do 1,000.
I think also it's, yeah, I think you would just do 1,000.
Okay, so you do 1,000 times 4.2 times 5. And then
yeah, exactly. You would, yeah, and that's what you would do because the heat gained by the water is the heat lost from the cashew. So yeah.
Okay, so 1,000 times 4.2 times 5 for the cashew, that's 21,000. And then 2,000 times is it just 4.2 times 5 again?
I think so, because 5
okay.
points temperature increase.
Okay, yeah. So it's just, so for the cashew, it's 21,000. For the marshmallow, it's 42,000. But since for the marshmallow, it's 3 grams, and we're looking for 1 gram of each, you do 42,000 divided by 3. You get 14,000. So that's obviously less.
Got 5,000 here, right?
No.
Or no?
21,000.
Yeah, 21,000.
So 14,000 is less than 21,000. So the combustion of the cashew should release more energy than the marshmallow, which is what it says. Cool.
Well, this kind of gives you your answer to your previous question.
Which one?
About H2O2. Hydrogen peroxide.
Oh, yeah, I didn't even notice. I was reading the bottom of the question first. Okay, which one is being oxidized and which is being reduced? So O2 is being oxidized and...
What?
Huh?
Doesn't it stay the same?
Oh, wait, let me think. So I thought it was being... But isn't it in O2 it's 0? It's not 2 minus.
Oh, yeah, no, sorry. I'm being dumb. Yes, that is 0.
So in 2H2O2, like it should be, so O2 is -4, right?
Yeah, essentially, the net is -4 here.
And then times the 2 for the coefficient, right? So -8. And then for
oh, I see what you're doing. Okay, -8, and then this would then be 4 plus. Wait, but how does that work? Shouldn't it? Oh.
Oh?
I don't think we do. Wait, what are you doing? I'm kind of confused.
I was multiplying by the coefficient. I don't know if you're supposed to do that.
I don't think so. Wait, no, you would, because that's representing the number of electrons.
Okay.
Yeah,
So 8. So -8. And then on the right side in H2O, it's -4 if you multiply by the coefficient. So it's definitely being oxidized.
Yeah.
I guess if it's being oxidized, doesn't
No, it's gaining no, it's losing electrons, right?
Yeah, so it's oxidized.
Oh.
Right.
Oh, but what about? Oh, wait. Never mind. So then, let's look at H then, and see what happens.
So in H2O2, is it like H2? Like, is it that H also has a charge?
Oh, yeah. The H also has a charge of +2 here, right? It would have to be that case.
It does? Okay.
Yeah, because 2 minus is the 2 minus for oxygen times 2 becomes 4 minus, so the H2 has to make up 4 plus. So each is 2 plus.
But okay, I looked
Maybe
at
I think there's a special rule for hydrogen peroxide.
Wait, let me look at H2O2. Like, is it called partial charges?
Oxidation numbers. Here, let me see.
Oh, that's what it's called. Okay.
Oh, sorry. So here's the thing. This is where the exception for oxidation rules is in oxygen. It's usually -2, except in peroxides. And in peroxides,
well, that's fun to know.
In peroxides, it is
-1.
I think it's -1. Yeah,
Okay,
each oxidation.
Okay, so that means, then the answer makes sense. So if it's -1 here, and then it's -2 here, then that means that it's being
gained electrons, and here it obviously lost electrons.
Yeah, so it's being both oxidized and reduced. So let's see. Okay. Oh, same one. Nice.
O2 gas produced. Pressure the flask after 4 seconds.
Wait, what is this given in? Like, what is this? Like, what is this?
So I think on the left it's time, and then on the right it's concentration of H2O2. So
Concentration, like liters?
no, molar.
No, mole, okay.
I believe.
Molarity? Is it
Yeah,
molarity?
molarity.
Oh, so it goes from 2.7 to 1.7. This is really weird. Okay.
So it's losing 1 molar.
Mm-hmm.
And it's 1 liter is decomposed, right?
It says 10.
Oh, sorry.
Wait,
Well, it's a
no.
10-liter flask.
Oh, okay.
That's
So,
1.
oh, okay. So then pressure would be cut in 10, right? I mean, like, divided by 10.
I would think.
Okay.
I'm not sure.
Okay, I see. So, okay, we're losing 1 mole, and then 1 mole exerts a pressure of 24 atm in 1 liter.
In 1 liter, right?
Yeah. So then, since it's in 10 liters, it would be 2.4 because you're dividing by 10.
Yeah.
I'm guessing it's gonna lose. I'm guessing it's gonna. Wait.
1 mole of gas in 1 liter exerts a pressure of 24 atm. Okay, so that means 1 mole of gas in 10 liters. So PV equals nRT. So if volume increases, then pressure decreases. So the pressure that we saw initially is going to decrease by a factor of 10. So 24 divided by 10 should be 2.4 as you suggested. Yeah, I would choose 2.4.
I don't know. I'm not sure about this one. It's 12. No, sorry, 1.2. It's 1.2.
1.2.
Okay, I was thinking because it's 2 H2O2 here and it's O2, and it is the O2 produced.
That's probably why.
Yeah. So I'm guessing you divide by 2.
Okay, yeah. We just forgot to divide by the 2 because we were looking at H2O2. Right?
Yeah. Okay. So you divide by 2. Okay. I see.
Can I see the reaction one more time? The equation for the reaction. Thanks. It's kind of weird.
We don't know. Like, how would we know this?
This is linearization.
Yeah, but like we don't. Are we supposed to plot this ourselves?
Well, the way you would know is by saying, well, you look at the differences. The difference here is 0.6, right?
Oh, and then it's
Here is 0.4.
And then 0.3.
0.3.
Okay.
So that means but this is inconsistent. This looks really weird. Oh, wait. That would be 0.2. That would be 0.1. The difference between those two, that's 0.1.
Okay, so it's second order?
Well, yeah, it's second order, but also if you look at the equation itself, I think that makes sense. The D also makes sense because
it says it's first order.
It's first order.
Oh wait, I think I got it. I got it. Yeah. Okay. Wait. Oh, okay. I did 1 over. I did like 1 over the differences.
Yeah. I'm so sorry. Yeah, that's. I don't know. I was looking at the. Yeah.
I did 1 over the differences, and it's like it's it would be linear. Like, I mean, it would be
Yeah,
like,
yeah, that's exactly what you're supposed to do. You're not supposed to do what I was doing.
okay, I did 1 over, and 1 over gives you like the exact same number. Like I got 0.833. So if it's just like a horizontal line, that means it's like the one before that. Because you're supposed to get, by straight line, it doesn't necessarily mean a horizontal line. It just needs to be linear.
Wait,
Yeah.
so the answer should be B though, right?
Yeah, I'm saying like when I did 1 over, I got like a horizontal line. And
okay.
so if you did, what I mean is if you did the like the.
Yeah, I know what you're saying. I understand. You get a straight line instead of a.
If you did the integral, you're supposed to get a linear equation.
Yes.
Yes. So it would be this one, ln.
Wait, if you did the integral, you would get a. If you took the derivative of ln H2O2, you get a.
You get this one.
You get that, yeah.
If you do the derivative of a linear equation, you get like just a constant number, which is what I got for
that. Okay, yeah, that's
one.
why that wouldn't work.
Yeah.
Whereas this one, if you take the derivative of ln H2O2, you'll get 1 over concentration H2O2. That's the rate at which the rate changes, I believe.
Yeah, okay. Mm-hmm.
Which would be, so that's why it's first order. Okay.
Yes.
Yeah, I think for first order, second order, third order, it really helps to think of it in terms of calculus and in terms of linearization. I think obviously I'm out of practice, but as you can see clearly. But I think if you know that math, it's good to think of it that way.
Okay, let's just do this one and then we can stop. Okay, it's thermodynamically favorable. Okay, that means that delta G should be negative, and okay, it's going from aqueous to liquid and gas, so that means I think
that's good.
More disorder.
Yeah, more disorder.
So that would be positive delta S.
Yes.
So I'm guessing it's B. Let me check.
I don't know why I say good or bad. It's good
and
bad.
Yeah.
That's how I think of it in my head. Yeah, I don't know. It just helps me. Yeah.
Okay, it's B. Actually, let's just finish up the page. So let's just do this one.
Sure.
So standard entropy change is positive. Oh, okay. This should be pretty easy, I think. Like I said, I just look at like gas and liquid. So this is going from gas to liquid. So that's negative
Yeah.
It's negative disorder. And then this is going from solid to solid and gas. So that's good. And then we have gas and solid to solid. That's bad. And then
I think the way I define good is energetically favorable, and that is that's how I define it.
And then I deliberately skipped A because it had gas to gas, but if you look at it, it's basically like 3 pieces going to 2 pieces, so that's less disorder. So we don't want that either. So C would probably be the correct answer. Let me check. Yes, it is C. Okay.
I like these questions. We can.
These are really easy. These are pretty good. Yeah. Okay.
Okay. Pretty solid. Yeah. Pretty solid session there.
Okay. Let me stop recording.
Yeah.
Bye.